Welcome all to today's ASRG World Webinar. We have the 1st of April 2021 and we are streaming from Stuttgart in Germany. Thank you for being with us. First of all, let me briefly introduce myself. My name is Sven Schran and I am coordinating with ASRG the European locations. ASRG is now 3.5 years old and I joined a bit more than 2 years ago. I have worked in the automotive industry just for more than 13 years and started to take care about automotive security more than 4 years ago. Today, I fulfill a role as product security officer in engineering of complex sensors for the Robot Bosch Group, which is one of the biggest automotive suppliers in the world. Just quickly, the Automotive Security Research Group, or short ASRG, is a non-profit organization focusing on the advancement of the automotive security industry. It is an open community to support the combining of two complex areas of competencies, the IT security and the automotive business. This community is for you, the automotive engineer, the IT security specialist, the security researcher, the beginner, the hobbyist, even for the people that are in the wrong YouTube channel. The entire organization is built on volunteer efforts of the administrative team and of course yourself. ASRG is mainly based on 3 important pillars which represent our core values: sharing knowledge, enabling networking, and valuable collaborations. We are trying to remove the boundaries that can occur in the automotive security industry. This means, for example, communicating about relevant publicly available information, finding ways to learn together, finding good solutions, making best decisions, because at the end of the day, we all together have a joint purpose to keep our customers, our families, our friends' data safe and secure when they are using automotive-related products or services. And this can only be achieved together. If you want to get more involved, make an impact on the industry, start your own ASRG location, participate in a technical committee, or be a part of one of our projects, please reach out to us. You find out more about ASRG at our website www.asrg.io or send us just an email at hello@asrg.io. ASRG is just available around the globe. Today we are present in 40 locations and 21 countries, and we just reached more than 6,600 members, which is really amazing. On average, we have grown around 15% a month since ASRG was founded, and this trend continues steadily. Please check out if your hometown is just part of our network. If this is the case, you are welcome to join our local representation. If you don't find a location near of you for now, but think it would make sense to have an ASRG location in your city as well, don't hesitate and contact us. Before we come to our main presentation, I like to give an outlook to the next weeks, where we have again very interesting topics which we will provide to you via our ASRG World Webinar live streams. Next week on 8th of April, we have Ken Munro from Pentest Partners, and he will talk about a vulnerability disclosure program, how to make it work. Then on 15th of April, we have Professor Dr. Frank Kagel from the Ulm University, and he will talk about misbehavior detection and reaction in connected automated driving. On April the 29th, we have Victor Maginan and Kamal Kumar Singh from Continental, and they give us a talk about a view on the security supply chain. We are as secure as the weakest link. Then on 6th of May, we have Matthias Weber from SecOps Solutions, and he will give us a talk about vehicle key lifecycle management. If you think you have a topic as well which is related to security and the automotive world, and you would like to present it to our community, please contact us with your idea via cfp@asrg.io. Now, it's enough from my side, and I don't want to keep you tortured anymore because I'm sure you are waiting very curious for our main presentation. Like every time, in case you have questions during the presentation, please write it in the chat window. After the main presentation, we will have a Q&A session where we will ask Bogdan. And now it is my pleasure to welcome Bogdan Gradinaru, the head of cybersecurity at clockworkX. And he will present to us automotive cybersecurity for engineers with functional backgrounds. Bogdan, please welcome. The virtual stage is yours.
Thank you. Thanks a lot, Sven. Thanks a lot for giving us and giving me this opportunity to host this presentation here within ASRG Group. Good evening, good morning, or good afternoon to everyone hearing us or attending this meetup or this YouTube live stream. Thanks. So let me ramp up.
Sorry, Bogdan, I think you are mute.
Oh, yeah, now it's okay.
Yeah, now can you please start again?
Sorry. So first of all, thanks a lot, Sven, for giving us this opportunity to present here, and welcome everyone attending this one. So either in the meetup or via the YouTube stream. Few words at the beginning about our company. So we are a small startup located near Munich, so in southern Germany, with the main areas of activities focused on two pillars, basically safe and secure systems and predictive and reliable operations. Yeah, especially in this pillar or this team within this pillar, so safe and secure systems, we are a couple of functional safety experts, so mainly with safety background, stepping into the cybersecurity, so mainly into, or firstly into the cybersecurity management area and everything having to do with the CSMS certification and with the automotive cybersecurity standards, so the ISO 21434, with which will be the main talk nowadays. And we are doing diverse consultancy projects for different industries and for different types of stakeholders and OEMs. Apart from that, we are also having pretty close collaborations with the technical university in Munich here, so with the institutes of for ethics in artificial intelligence. A few words about myself. So I have more than 14 years experience, most of them in automotive industry, with a short gap within machinery field in the machinery industry. Since about 6-7 years, I've been dealing with functional safety, mainly with ISO 26262, but not only with that, so also with the general, with the, let's call it mother safety standard, the IEC 61508, also the machinery safety standard, partially also the railway. I used and I still use to do coaching and training activities in regards to safety. I also performed myself, and I've also been part and supported different types of safety audits and assessments. I've been myself member some while ago also of the AUTOSAR VPA3 functional safety group. And since about 1.5 years, I also stepped into the field of cybersecurity, mainly in the automotive cybersecurity. We started here also to have consultancy projects in regards to VDA TISAX audit and preparations for audit, also CSMS, gap analysis, CSMS management, so the 21434 standard, and also the general ISMS standard. The presentation today will be mainly could be basically split in two parts. So at the beginning, the plan would be to give you a brief overview about the two standards. So ISO 26262 in functional safety and the 21434 in cybersecurity. So a bit about their purpose, about their role, about their historical background, about the main driving forces, which after all, eventually made them to come into being. Also, short overview about the structure of the standard with the clauses and with their tailoring on the V model. And then the core part of the presentation, the nitty-gritty, more or less, of the presentation would be to exemplify those two standards, mainly the risk analysis, so for safety and for security based on a concrete system. And for that, I use the lane switch assist system. Yeah, and all those steps here below, so they will they are concerned to that. At the end, I also, before concluding, I would also like to present some general aspects beyond this risk assessment part. So some things about different engineering concepts about safety versus security, cybersecurity management in automotive, and for sure at the end, at the very last end, the conclusions. So let's start with the definitions. Functional safety, here to the left, is defined as actually being the absence of unreasonable risk due to hazards caused by malfunctioning behavior of electric and electronic systems, whereas cybersecurity, instead of being focused on car functions, so item, what is called in functional safety, is rather focused on assets and threat scenarios. Yeah, so basically, cybersecurity for automotive, as it is defined in the 21434 standard, is that condition or that state in which the assets are free from cybersecurity risk in regards to the corresponding threat scenarios which the OEM, respectively the stakeholder, selected them. And also still focused on electric and electronic components, so in the same manner as functional safety. This is a good starting point because this sets up the groundwork for the future steps, because they have slightly different approaches. So as we will see it throughout the presentation, functional safety, then as I said, it starts with the car function, yeah, whereas the cybersecurity, it starts with the threat scenarios. Therefore, in cybersecurity, it's really important, it's really crucial to have a pretty robust set of threat scenarios or a threat scenario catalog. A bit further clarification of the main topics or the main notions involved previously in the definitions of the tools. So basically, risk in functional safety as well as in cybersecurity is basically given by two factors. So the impact, what in functional safety is called severity, and the attack feasibility, what in functional safety on the other side is considered as the probability of harm. Yeah, so how exactly this is calculated, we are going to see that a bit later in a more or less systematic way. Here also the definitions for threat scenarios and assets as the standard considers them, as the 21434 defines them. Here is important to keep in mind that they are free to be defined by the OEM or by the stakeholder. Yeah, so stakeholder basically is has the freedom to select, to pick up whatever it considers to be valuable for itself as an asset, and also based on that to create the threat scenario catalog as described here. And the list of terminology of this parallel terminology could go further. So basically most of the typical terms in functional safety may have a sort of correspondent into cybersecurity. Let's have a look. Let's have a short look about the main purpose of the safety and cybersecurity and their approach to the risk. Yeah. So above functional safety, its approach to the risk, or at least the typical approach as defined in the ISO 26262, is to reduce the risk to a minimum acceptable. So this minimum acceptable is basically a societal factor, and it depends obviously on the social circumstances when it comes to, let's say, collective acceptable risks. And this is stripped down, or this is then refined basically to individual types of risks, which are assigned to individual types of car functions. The risk approach is based on a risk matrix. This is the same as for functional for cybersecurity. The only, let's say, big difference is that in ISO 26262, it is mandatorily required to assign some assurance levels to different types of risks. So those are the so-called, the famous ASIL levels, which then they are basically, they're given some top level requirements, which in functional safety are called safety goals. And those are basically stripped down to requirements which have to be allocated to hardware or to software. There is this option in functional safety to reduce the risk via decomposition. On the other side, in cybersecurity, so as we mentioned, the whole cybersecurity cycle starts with the threat scenarios and with the valuable assets for the stakeholder. And here it's rather the risk to be managed instead of being reduced to a minimum acceptable. There is also this cost benefit. And here cost, I mean really in terms of financial cost involved. Whereas the financial costs in functional safety, they don't play any role. So they are not involved at all in, they do not affect at all the ASIL, for instance, for some requirements. They do not play at least any essential role. Whereas here it's a permanent, let's say, back and forth game in between the costs and the benefits, yeah, because in automotive, as we may see it further, it might be that many factors are already costly deterrent for an attacker to actually avoid from the beginning on an automotive cybersecurity attack due to the high cost of, I don't know, getting a car, getting certain components, car components. Besides that, the cybersecurity automotive standards also relies on the V model as well as the functional safety. So V model It's also important for ISO 21434, and also it builds up a lot on the existing quality management system. Risk in cybersecurity, maybe compared to functional safety, is rather more dynamic, and it has to be tracked continuously even after production. Yeah, so this is outlined also in the standards in figure E1, so in the annex of the cybersecurity standard. And the main meaning of this figure is basically to highlight the difference in between an assurance level. Yeah, so here the CAL would be the abbreviations for cybersecurity assurance level, and the dynamic nature of the risk, which can evolve and which can change all across the typical product life cycle phases. Yeah, so as we depict here, so it could be that at the beginning we are dealing with an initial high risk, which is beyond the typical, let's say, acceptable risk, so it has to be lowered via analysis and via concepts. And then once the concept is done, and once the requirements are created and then assigned to typical components, so either hardware or software, once basically the production, the development phase starts in, then it could be also that cybersecurity flaws are discovered on the fly. Very important here is that it continues even after the production phase. As a matter of fact, the operation and the maintenance part within the car components life cycle plays an essential role. So here you can imagine that this part here, so it can be repeated many more times during the car life cycle. So this may even not stop till the end of the car life cycle, till decommissioning. That's why it was also not so easy. So it's not as easy as in functional safety to assign a typical assurance level or a sort of equivalent of ASIL for cybersecurity risk. Before stepping into the history and the historical background, before having a short overview of the historical background of the two standards, so basically some few words about the main driving forces for this joint ISO SAE 21434 standard. So as any ISO standard or as any standard, it is essentially meant for a few things. So one of them is basically to provide some guidelines, basically to provide the necessary checklist throughout which, so basically due diligence can be performed by an auditor to make sure that a system then basically fulfills minimum requirements in regards to engineering as well in regards to management. Another thing, another essential aspect about the driving force of this standard is basically to harmonize former or pre-existing efforts, research as well as driven from the industry, so academia as well as industry-driven cybersecurity research, and to harmonize them in order to use the same type or similar type of terminology. Yeah, and also to create common and standard processes for collaboration in between different tiers and stakeholders. A bit about the historical background of the standards. So here below is basically depicted the whole history of the functional safety, ISO 26262 standard, and above there is, starting at some moment in time, so mainly 3 years ago, beginning of 2018, the 21434, but also there catched up also some pre-existing efforts in regards to automotive cybersecurity standardization. So a few words about functional safety. It started everything with the, as I said, so-called safety mother norm, the IC standard 61508, which has been released far ahead of 2005, and which was, even into automotive, the state-of-the-art functional safety standard till 26262 came into being. In 2005, there was basically the first working draft of it. Then it came basically the typical ISO lifecycle steps, so with the typical types of drafts to be approved internally within the ISO consortium and also released towards. So coming then with the committee draft, then the draft international standard, which actually precedes the FDIS, and then it comes the first, and then also the final draft international standard. Then the standard can be released in case of 26262 due to the fact that there are many guidelines and many informative parts of the standard. Those came afterwards and they were released separately while after that. And then basically somewhere around 2012, so the standard was completely released, the first edition. Not later after that, it started already the works to the second edition. So this followed basically the same steps as for the previous one, and somewhere beginning of 2019 was basically the second edition, so officially released. In case of 21434, this started more recently, so 3 years ago, and now we are in a phase in which the final DIS was released, I think a few weeks or 1 month ago. Before that, one of the main standard and also one of the main driving force of the 21434, also one of the standard which the 21434 took a lot over, was this SAE standard J3061. It was rather a guidebook, yeah, and it had also many informative annexes and many reference also to 26262. So it was also meant to bridge also the gap through the functional safety standard. Before that, there were many types of research which were triggered by different OEMs, which were more or less regional, triggered across Europe, maybe across United States. So Evita focused on hardware, Sevecom focused on secure vehicle communication, Heavens focused on secure software, which then afterwards had to be harmonized in a single ISO standard. Quick overview about the two standards. So 26262 in terms of size is far bigger than the 21434, and implicitly requires far more effort to be implemented, and implicitly it requires higher costs for that. So the 21434, that keeps basically the same main aspects. So it's about work products, it's also about requirements, some of them, as we are going to see, mandatory, some of them advisory. All in all, it's around, yeah, a standard maybe 10 times smaller as the functional safety one. just a short overview about the 26.26.2 structure. So as I mentioned, big standard, a very broad one, tackling basically the complete V model and the complete product life cycle. Some of the parts are entirely dedicated guidelines, and they are completely informative. So they do not have, let's say, normative power. They do not have legal power as part 10 and part 11 here. Part 11 and 12 have been, by the way, additionally included in the second edition. So they appear only in the second edition, were added into, since also this extension for motorcycles has been done. On the other side, the 21.434 is laid out on the same basic aspects. So it's still about general notions, about general terminology, general considerations, management, organizational one, and also project-dependent management. So for that, we've seen previously there is an entire volume. It's an entire part dedicated for that in functional safety. Risk assessment methods. So here there are basically the HARA steps described in continuous cybersecurity activities. This is indeed an important part. This is the part that we discussed previously by this dynamic aspect of the cybersecurity risk. This is basically those are the cybersecurity activities occurring after development. And obviously, so the concept and development phase, much thinner as compared to functional safety. So only one clause dedicated to product development, whereas in functional safety, so basically 2 volumes separately dedicated for software and for hardware. And for the rest, so more or less the same type of activities and the same type of clauses. Yeah, so distributed cybersecurity activities, this has to do with project-dependent management. This is also considered in part 2, for instance, of the 26.26.2, and also the informative parts and the explanatory annexes. One of the first potential interactions between or with cybersecurity are already introduced in part 2 of the 26.26.2, and namely in Annex E. And this is basically structured on 4 main aspects: on management, on concepts, on product development, and what happens after development, so basically, or even after production, so basically maintenance and operation phase. In the current example that I showed previously, so I'm going to tackle rather this concept part. So since this is going to refer a lot on similarities and the differences and aspects to be taken over back and forth in between TARA, threat analysis and risk assessment in cybersecurity, and HARA, so hazard analysis and risk assessment in functional safety. Both of the standards, both of the approaches, so laid out on the V model. Here basically picture depicting so the corresponding functional safety, so here with light blue activities laid out on the V model, also the supporting aspects, and also the after development aspects for functional safety in dark blue, so basically the corresponding cybersecurity activities. So there is perfect match in regards to the steps to be laid out on the VE model of the tools of functional safety and cybersecurity. That's why that's permanently this those thoughts that there are many aspects to be cross-referenced from one field into another. Also, to end with the introduction to the standards, so also some few aspects related to the interpretation of the requirements in functional safety. We are very accustomed with this type of tables here. So this is one of the essential parts of the standard, because basically in order to be ISO 26226 compliant, you would need to fulfill the highly recommended methods, so namely the must ones with the plus for the corresponding ASIL for which a car function has been assigned. This is not so in cybersecurity in 21434. This is, at least in my view, simplified and a bit better clarified, because the type of requirements are split in these three groups. So there are the mandatory requirements labeled with as requirements, and then there are the recommendations, which could be interpreted as should requirements, or could be taken more or less as the plus methods from functional safety. Also, another interesting and also maybe the same time intriguing aspect of the 26262 is the fact that the standard has two types of methods. So alternative methods are methods that basically are mentioned in the same table with letters following the numbers. That means that one of the two methods can be selected, so not all of them are mandatory. And in case if they are numbered here, they're labeled with numbers, then the ones having different numbers, they have to be separately implemented, mandatory. So for instance, here one method from the ones labeled with 1 has mandatorily to be implemented for the corresponding ASIL, for instance. One from labeled with 2, and obviously the last one labeled with 3 has to be done anyway. Okay, let's get into the system. Let's get into the lane switch assist system, and let's see a bit the cross references in between the two types of risk analysis. Before stepping into the example, I would like here to show up kind of disclaimer, so to point out and to stress on the fact that this example, it was more or less invented for this presentation purposes, and may definitely not be correct, may definitely be interpreted in some different ways. So it's definitely simplified, if not maybe oversimplified into some areas. And in regards to product engineering, may definitely be done in some different way. The main aspect with it is basically that the methods and the reasoning steps to illustrate the risk assessment in both in functional safety as well as in cybersecurity, they are as in this example. So this example is mainly to illustrate the risk assessment method and the reasoning steps behind it. Also, the network topology that I choose there, they may definitely be interpreted in some other way. So please do not take this example as being, let's say, technically correct. Why lane switch assist? So for a couple of reasons. First of all, that it's a highly complex system. As a matter of fact, being semi-autonomous systems. So I use that in order to reflect different types of warning strategies and also on degradation strategies for the system, as I'm going to show afterwards. The point that I mean here below, it's also a system where it's very, very challenging to separate different car functions, to pick up different types of assets, or to make up your thoughts into consider something within this system as an asset. And it also has a different impact on different cybersecurity aspects. So it's not only related to safety, but it may also impact privacy and the financial cybersecurity aspects. So basically, this is, if you are familiar with the standard, with the 21434, this is bit of change, or let's say enhancement, or a different use case example of this headlamp system presented in the annex of the 21434. So a couple of basic aspects about this lane switch system, which I personally assumed for the purpose of this presentation. Under which types of conditions can be activated, which types of interfaces does it have, where does it get mainly the environment data, how can it be and by which systems can be activated, correspondingly deactivated, and those I call them also for the sake of this example some sort of degraded types of functions within this main customer function, which is lane switch assist. So when this is not working anymore, then the assumption is that it can switch to a degraded mode of the lane switch assist, which can be the lane keep assist, which doesn't focus to change the lane. It only focuses on keeping the vehicle straight on the current motorway lane, and even more degraded on a lane departure warning system, which only warns the driver in case the car basically deviates too much from the lane. But it's still, as we are going to see in the next slides, it still provides lateral automation control function. Related to types of automations, so in order to clarify or to better illustrate where and how could fit those customer functions, as for the LSA here, and also for those sub-functions here within the typical SAE automation levels, I basically assume that the lane switch system would be a level 3, so basically a conditional automation system, basically providing the lateral automated control of the vehicle as well as the environment perception. And the other two sub-functions providing only automated lateral control. Okay, so safety starts, and functional safety risk analysis usually starts with the car function, with the main car function, which in the standard is called the item. So at this stage, there have to be defined a set of typical properties of the selected car functions. So this could be also differently interpreted by one OEM or by another. But this should be, in any case, everything that implements a function at the very end of the vehicle level. And at this level, that should be defined some basic aspects, as for instance, the operating modes or states of the vehicle, a functional description of the function, as well as with the functional interfaces and dependencies. Eventually, maybe also operational scenarios or operating scenarios, as we saw in case of our LSA. So this would be in typically the highway driving scenarios. And also it could specify some technical aspects and namely the types of systems, the types of controllers or the ECUs to implement the functions, and the types of interfaces between them, and at technical level. So whether the interfaces are CAN or Ethernet or whatever, OBD or wireless or whatever. Yeah, here is what I try to depict the functional description of this LSA systems, which is highly complex, but as I said, so I did that on purpose, so to illustrate as many interfaces as possible, and also to showcase different aspects of how can they be impacted in regards to cybersecurity. So not only when it's about safety impact, so the typical case in which the lateral control via the LSA function is lost, or it's not done appropriately, but also private aspects in the way that maybe driver personal data could be stored on the function or on one system or one controller belonging to the function. Maybe also OEM relevant data could be stored on some controllers. Part of this item, also road infrastructure data can also be stored on systems interfacing quite closely with this LSA function. So this is getting a bit detailed here with a system description. So this has to be a description at the system level, so more technical than the previous one. So here, so really the concrete types of the ECUs or of the car controllers should be described, and also the interaction with the driver. Yeah. So here, as you notice, also possible interaction with the backend server, which this may open up a broad range of threat and cybersecurity threat scenarios. Okay, after the two types of item descriptions are done, so at the functional, respectively at the technical or system level, so the involved controllers or the involved technical components, they can be listed down, and a short description on how they contribute to the LSA, to the lane switch assist should be provided. Yeah, so this is also a typical step in functional safety analysis when doing the item definition. So here I selected so for presentation purposes some different functions which those systems could perform, and which could contribute after all to the lateral control of the vehicle via the LSA function. Also here some interfaces with two other customer functions, so automatic emergency brake and traffic jam assist. After the item definition has been performed, the very next step of within the functional safety process is doing HARA. And HARA consists basically on 5 main aspects in 5 steps. Yeah, at the beginning, so based on the car functions or on the description from the item definition, Then there is the system behavior selected, and basically via those guide words, yeah, either too low, insufficient, too high, complete loss of the function, they're derived out of them. So basically malfunctions for those functions. And those malfunctions, they are taken over some different scenarios, which are normatively prescribed by the standards. So the types of scenarios, well, at least the basic types of scenarios in regards to location, to type of traffic, to type of road condition, to environmental conditions or vehicle usage are prescribed in the annex of the standard in part 3 of the 26.2, and those malfunctions have to be assessed based on that. At the end of all this chain, there comes some hazardous event, which is a risk, which is the end risk, which has to be assessed in regards to safety as per 3 parameters. And those are the very famous in the functional safety world, the severity, exposure, and controllability parameters. There are also prescribed how those values can be assigned, when you are allowed to put an S3 and when you are allowed to put an E4 here, so I'm not going to step into the detail. Here the controllability parameter, this is a bit trickier one, especially in the context of semi-autonomous driving functions, as it is this one. Since the assumption is that here the LSA should basically steer the vehicle on itself without relying on the drivers. So basically, I stuck the controllability parameter here to the worst case scenario, so namely to C3. And out of that, they're coming the typical ASIL, Automotive Safety Integrity level, which are from A to D, A being the lowest critical one and D being the highest critical one. So in our case, both of them. So the main function of the lateral control, as well as this warning function of the lateral control, are classified with the highest one. And based on that, we should write requirements, which are the top level requirements, namely the safety goals, functional safety. I labeled here in red, so the aspects which can be taken over to cybersecurity analysis. So we will get back to those aspects here in red when doing the HARA on the other side. Here a brief description of a possible warning and degradation concept for this LSA. So here important thing is that is this fault tolerance time interval. So this is the time when basically we are allowed to hand over the system from an unsafe state, which may occur once the error has been entering the system, has been occurring, till this is safely handed over to the driver. Or here could be interpretable. It depends on what we consider here the safe state. So safe state could be, here can be degraded, could be lower critical and higher critical safe states, in the way that we assume that initially we are basically switching off the complete automated control of the LSA function, and we are basically degrading to a sub-function of the LSA, like this lane detection warning system, and we inform the driver, so gradually, firstly maybe acoustically and then visually, and then basically if we cannot, or the system cannot handle it at all, then it needs to completely hand over the control to the driver, which is depicted here. So here basically a resume of the essential aspects which can be relevant for the cybersecurity analysis. Yeah, that's why I call them the takeaways. Yeah. Let's step into the cybersecurity analysis. So as I mentioned, this starts with the assets and the threat scenarios. This starts a bit differently than in the functional safety. There are the assets which have to be defined at first. Then a robust set of threat scenarios have to be defined and have to be matched with the relevant assets. So which assets can be attacked, which assets can be reasonably attacked under which threat scenarios. This would be the next step. And then the cybersecurity risk consists of basically two steps. Yeah, as I mentioned at the beginning, determining the impact, so the gravity or the severity of the damages that can be done on the assets, and the possibility or the probability to exercise an attack, which is called the attack feasibility. And both of them, they come into a risk value. And then after that, we need to select the risk treatment. Which one of those options could be the risk reduction, which will step into the technical aspects, which I mentioned here as the product related ones. Yeah, because there are many options beyond the risk reduction. For instance, another option would be the risk transfer to some insurance company. Yeah. And then basically, if this is written down in the CSMS protocol as being transferred to some insurance company, and if that insurance company can sufficiently assure that the risk is sufficiently lowered by that, then it's no technical approach is needed for that. So basically no cybersecurity concept, no requirements may not be needed in that case if this is an option to be taken. So asset identification, how the OEMs usually do the asset identification. For that, it's recommendable to use a certain taxonomy. Yeah, so the assets can be defined in terms of functions. They can be defined either in terms of vehicle functions, in terms of system functions, in terms of controller functions, in terms of communication messages. They can be also defined in terms of data. Yeah. This could be communication data, communication traffic, static data within the systems, external or road infrastructure data. The essential part is that those assets, their cybersecurity relevance, it needs to be determined based on three aspects: confidentiality, availability, and integrity. So this is the famous CIA triad. And whenever one of those three aspects of those assets can be influenced, then this has to be taken as cybersecurity relevant asset. A second step within that, it's not explicitly mentioned in the standard, but this is what typically the OEMs do. It's also to depict the typical user interfaces that those assets can be accessed through. Yeah, and user in this case could signify very different things. So a user could be a car user, a user could be somebody from the workshop, a user, I don't know, could be an attacker or could be a hacker. But also an important step within the cybersecurity analysis is to determine which types of interfaces can be relevant for different types of functions. So here I tried to select here. So once again, I picked them up only for presentation purposes here, they may be different, they may be selected in a different manner, and I picked up here more or less the ones which may be relevant for our LSA function. After that, threat scenario catalog should be defined, and this could be done independently of any type of asset. For that, it could help also a certain type of taxonomy or a certain threat model to derive those threat scenarios. So as I used here, the theft types of threat scenarios, the manipulation or tampering, the privilege escalations or access gain, the complete denial of service, the information disclosure. This could be interpreted in a different way by different OEMs, but the essential point on that is that they have to follow a certain taxonomy, or they have to follow some threat modeling rules. Yeah, and here also the same is valid for the assets. So here also, as we mentioned before, the assets can also be clustered based on those modeling or based on this taxonomy. Could be selected as a component, could be the whole car or a car function, which would be in our case exactly that one. Could be intellectual property belonging to the OEM, could be PII, driver personal identification information, or different aspects. Out of that, so till now, we've been speaking only about general assets and threat scenarios without function relevance, without item relevance. Yeah, because when the cybersecurity analysis starts for a certain item, then it has basically to build up upon the item definition from the functional safety. So the very first step in functional safety. And based on that, so the types of threat scenarios are narrowed down to the relevant ones, which basically which may affect our item. Once the relevant threat scenarios are identified, in our case, so here I selected two of them highly relevant in regards to safety, and also two other ones in regards to other different aspects. So theft of personal data, so this would be rather relevant in regards to privacy aspects, and also the ADAS function here in regards to financial aspects. The impact has to be determined in regards to those four aspects. So this is standardized by 21434, that each relevant threat scenario have to be its impact has to be determined based on the four aspects. For the safety aspect, it can be taken one-to-one, the severity factor from the functional safety. So from the previous HARA we saw. So if you remember in the previous slides, for the HARA, for the corresponding item, we picked up an S3 level for the severity. So for this LSA function here, that's why it stays here S3. And here, if it sounds familiar to you, so those threat scenarios, especially the ones that are safety relevant, so where the safety aspect, where the safety impact is labeled as is classified as being severe. So here the hazardous events, the risks from the previous HARA may help a lot in determining or in better shaping the threat scenarios, in better determining the threat scenarios. That's why also this cross-reference is needed. So that's why probably before determining the relevant threat scenario set is also required, is also advisable to look into the HARA and to look into the hazardous events determined over there. Till now, then there was basically the half of the cybersecurity risk aspect determined, which was the impact. And now we would need the second half of it, which is the attack feasibility. For that, we would need to get access to the system structure, and we would need to see the system topology. For that is what the standard calls the vulnerability analysis. The cybersecurity ISO 21434 refers to two types of analysis, the top-down and the bottom-up. So top-down deductive reasoning, starting basically from the effects, coming down to the root causes. And for that, basically, is necessary to have the item topology or the item structure. So it is basically the system description of the item which we saw previously. In that case, it may help a lot. So an existing failure tree analysis of the item. Yeah, this could be taken to some extent one-to-one for this top-down vulnerability analysis, namely to some attack tree in order to to estimate, in order to assess the possible root causes which may influence this top event, yeah, which was previously, so we had them labeled as safety goals, but they can become, as we are going to see also, cybersecurity goals, as long as they are relevant to the safety, as well as long as this safety impact, as we saw it previously, is relevant for them. And this is a standard method in safety as well as in cybersecurity. There are standard fault tree analysis as well as standard attack trees. In that case, it could be for those severity, for those cybersecurity goals with safety impact, it could be taken basically the one-to-one, the system paths from the functional safety. Here the AND gates, they basically show that this top event here can be influenced or can be affected by both of the lower bottom events here separately, so they don't have to occur simultaneously. An AND gate, on the other side, is a top event which can only be influenced by simultaneous occurrence of the bottom level event. So here I forced a bit this example just to have an AND gate, so just to show that this could occur just for presentation purposes. But this basically is created using the system topology shown previously at the system description. The bottom-up vulnerability analysis, on the contrary, so basically starts with the individual component vulnerabilities, and for that there could be many different sources to tackle on that. So the ISO 21434 basically recommends certain sources which may be taken into consideration to investigate on components vulnerability. There is also established during the years also the so-called mixed safety and cybersecurity FMEA method, which is called the failure modes and vulnerability effects, which basically
assumes that takes into consideration simultaneously the failure as well as the threat modes of the components, and infers then threat or cybersecurity risk simultaneously to a functional safety risk probability within the same type of analysis. So it's that both of them can be basically run in parallel. So the safety FMEA as well as this vulnerability FMEA. Here, so basically the threat modes can be selected as we saw on the previous slide, considering the sources suggested by the standard as shown previously. And in this way, this basically gives the path, or this gives the way on how to assess this attack feasibility, this second half of the cybersecurity risk. And these were some examples that I've been taken, so basically one-to-one from the FTA respectively attack tree on the previous slide here. So if you remember, there were basically 4 bottom-end events which can affect the first safety respectively cybersecurity goal. And also for the second one, there were 4 end events, 4 bottom level events, which may affect the second one. And they can be assessed in regards to different aspects. Those are informatively mentioned by the 21434 in the annex. And they can be defined based on different attack probability or attack potential standards. Here I picked up only for example or presentation purposes the 4 ones. And here is basically the gravity or the severity of them labeled with colors. So do not wonder if the same numbers, they do not belong to the same color, because here the color is basically meant to imply the easiness of the attack. So the red one, that means that this could be exercised, corresponding attack could be exercised by low-skilled attacker. That's why it's labeled in red. The green ones, they are the ones which are basically hard to occur, or whose probability is rather harder to occur. And the numbers here, so I choose them more or less randomly. So for this presentation purpose, but they can be done based on various types of scoring systems for them. So there are standards for that. And in the end, for each attack path, for a certain threat scenario, it has to be an end result for that. And this result for each threat scenario, it has to be aggregated, it has to be condensed together, as we are going to see on the next slide. So out of the 4 ones, we need to take out a sort of average of it, which is to be used for the final risk determination. The same for the second threat scenario here below. So here basically the 2 ones which were shown previously. So the aggregate one is the mild, for the second one is the low one. I also added the other 2 ones which are not safety relevant, and also additionally to those 4 ones, another 5th one which may not imply a risk reduction at all. That's why I mentioned here that as a risk treatment option, which by the way is a mandatory thing required by the 21434, it has been chosen a risk transference. Yeah, and in that case, there is no need to specify any cybersecurity goal. There is no need to create a cybersecurity concept. So it's basically no need to delve too deep into those technical product cybersecurity aspects. Safety and cybersecurity goals. Yeah, I mentioned them quite often during the presentation. They can be assigned, the cybersecurity goal can be assigned. So in case, as I mentioned, in case a risk reduction is chosen as a risk treatment option, then a cybersecurity goal can be defined. So this is, by the way, an advisory requirement. And this can be assigned this so-called cybersecurity assurance level. So to some extent, sort of ASIL sibling in cybersecurity. It can also be defined for operation or maintenance, or more or less the after development and after production phases of the car. The main purpose of the cybersecurity validation, in case those cybersecurity goals are defined, is basically the test of those goals, yeah, which is mainly recommendable to be done via the penetration tests. On the other side, the safety goal is a mandatory requirement in functional safety. So once an item, car function has been, or a risk for a car function has been classified with an ASIL, has been classified as being safety relevant, then ASIL is mandatory to be defined. And this ASIL then is critical for the requirements following down the stream, yeah, down to hardware and to software components. Good. So here to conclude those parallel risk analysis, so for functional safety and for cybersecurity. So one close to the other. So the cybersecurity goals and the safety goals. What can be taken over from the one? How can the one basically help formulate the other? So basically here we saw, especially with the ones that have to do with safety, they can be formulated basically in the similar manner as the safety goals, specifying basically the typical cybersecurity attack. Yeah. Here the theft, I chose them for other purposes as safety. So basically this is the private sphere, the privacy aspect here impacted. That's why this call is basically assigned to cybersecurity goal whose impact is on privacy rather than on safety, and here rather for financial aspects than of safety, and also with the lower call level. So in regards to CAL and similarities with the ASILs, so I try to explain that, or I try to illustrate this on this slide shortly. So ASIL, which by the way is a very formalized functional safety attribute, it has different levels. So with the lowest critical one from ASIL A to the highest critical one to the ASIL D, there are management aspects which are more stringent once the ASIL is getting higher. Yeah, for instance, assessment or audits are only mandatorily requirements starting from ASIL C. Also technical aspects required once or which are more stringent once the ASIL gets higher. The CAL approach with that is to some extent similar to that, but I think, and it's not only me, it's the general consensus, that the standard needs to improve on that, needs to detail more on that. The standard, the 21434, the cybersecurity standard, is a bit too superficial in regards to those assurance levels. Maybe it needs to provide more info on that, more detail on that, but it's more or less the same approach. So the higher the CAL numbers, basically the higher the technical rigor and also the management effort to be put in. Good. So once this has been done, and basically the risk assessment part has been finished, has been achieved. So we are stepping into the concept part, into the product part. So I'm going to go pretty quickly throughout that, because the main purpose was to illustrate in parallel the risk analysis for both functional safety and cybersecurity. I'm going only to highlight some essential aspects from the one discipline and from the other. In functional safety, that's a big deal on how the safety goal is stripped down, and which method and which approach is chosen to strip this down, or to create requirements out of that. One of that is this the so-called goal structuring notation, which I, by the way, used here. So this is only for example purposes. This is one method on how to derive from the main safety goals, basically lower level requirements, which they need to be then derived or stripped down further down to components, to individual components. The same for the second safety goal. All of that shown on based on the complete V model, especially on the left side of the V model. So we have at the top the safety goal, which was, as we said, classified with ASIL D, and then the stripping down of it into lower level requirements. In safety, there is this possibility to lower the risk via this so-called decomposition, yeah, as is mentioned here. So this ASIL B of D, with the mention that they are sufficiently independent, and this is a big topic in the functional safety. So it's a big effort put in by companies, by stakeholders to prove this independence, and there's also a lot of science and work around this on how to demonstrate that one requirement may be sufficiently independent from the other. This is very important because ASIL D, in terms of technical implementation, is very costly. So there are some software methods which are mandatorily required for ASIL D, which are very costly, and which many OEMs or maybe even tier ones, they want to get rid of them more or less by this decomposition. Yeah, so this is one of the main purposes of this decomposition. Something like that doesn't exist in functional safety, in cybersecurity, excuse me. So the standard doesn't prescribe any lowering of the risk via this decomposition. The cybersecurity requirements, then they are basically the standard is not so specific in regards to that. So they need to be specified. Every company, every stakeholder who wants, after all, to get this CSMS certification needs to have a cybersecurity specification for the corresponding item. There's not there are not methods, and there's not so many requirements, at least compared to the functional safety standard, in regards to cybersecurity requirements. So the standard, the cybersecurity standard, it's pretty relaxed in regards to this aspect. Yeah, so here I try to split them in the ones that they are mandatory and the one that they are advisory, required by the standard. It is also the same thing in regards to the architectures. So there is no mandatory type of architecture prescribed by the ISO 21434, neither in regards to some specific CAL or cybersecurity assurance level, nor in regards to the final risk. The standard only recommends that the typical established solutions, they can be taken into consideration. But here the challenging aspect in regards to that is how to match this with existing safety architecture, because system architecture in safety plays a big role, and the 26262 mandatorily recommends different types of architectures for different types of ASILs. So this plays an important role. And then a challenging aspect would be how to cope that with the cybersecurity, how to make this fit with the cybersecurity. Yeah. So in case some cybersecurity relevant data, as for instance private keys or similar aspects, they have to be stored on separate unit or on a separate controller. How can they be considered within this overall system architecture from safety side? Test coverage in cybersecurity is indeed quite thoroughly specified. As a matter of fact, the test methods, the verification and test methods recommended by the cybersecurity standard in the annex are looking in a similar manner as the typical methods from the functional safety standard, the typical plus and plus methods. So here I try to depict a couple of them. So here on the right hand side, so basically the methods, the test, most of them test methods laid out on different CALs, on different assurance levels in the informative part of the standard, and their corresponding methods, which I selected from the 26262 on the left hand side, from the functional safety. Basically, is the same approach, is more or less a one-to-one approach, also in regards to the ASILs. So they more or less correspond one-to-one. What is taken here as CAL4, they may correspond more or less one-to-one with an ASIL-D for an ASIL-D method here. So the similar mindset was behind them. In the end, the validation as a last product lifecycle phase, the validation in cybersecurity is focused on the cybersecurity goals and to determine the validity of the goals and of those claims, which are sort of cybersecurity assumptions to be determined at the beginning of the cybersecurity life cycle, so when performing the HARA. And once we are at this validation stage, then it's worthwhile to also to compare and contrast the different types of validation tests. Yes, in functional safety, there are the fault injection tests. They are not only for the complete product validation, but rather they're also at lower levels. So they're also at system level, at hardware, software interface level. But their main purpose is to check basically the safety mechanism. On the other side, the penetration tests, they could be considered as a sort of sibling, a sort of cybersecurity sibling of the functional of the fault injection tests into cybersecurity. They are meant mainly to check the security mechanisms. And beyond the penetration test, the 21434 also recommends two other different cybersecurity validation methods, so the vulnerability scanning and the fuzz testing. None of the two ones is tailored or is laid out on any CAL level, so it's not so that for the highest CAL or cybersecurity assurance level, some vulnerability scanning is mandatory or not. So they are completely informative, completely advisory, recommended by the standard. There is a scarce mention of hardware requirements in the cybersecurity standard. This is a big topic in functional safety. For that, there are two volumes, two parts, completely dedicated to it. Whereas in cybersecurity, this is more left free to the OEM. Yeah, so there is no type of recommendation neither on these typical standard HSM levels for different hardware components. There's hardly a mention of the hardware notion within the 21434 standard. Software, it's also software requirements in cybersecurity standard. They're also pretty relaxed mentioned. There is no typical method recommended or highly recommended, as we saw in functional safety with plus or with plus plus in cybersecurity standard, but rather there are general recommendations or mandatory requirements in general in regards to general aspects of the programming or modeling language, as well as related to the detailed design or as related to the software design principles, as we see them here. After development activities, whereas in functional safety, this is an aspect which is not so much effort invested into it, at least compared to the effort invested within the development part of the life cycle. In cybersecurity, this is completely different. So this cybersecurity lives far beyond product development, and it is essential, if not crucial, also after development, and even after start of production. For that, there are dedicated clauses for that, as we saw, continuous cybersecurity activities. There are very important requirements for production or for maintenance, for cybersecurity production and maintenance after development. So this is, to say so, taken far more seriously in cybersecurity. And in the end, a couple of concluding aspects. The cybersecurity standard also deals with off-the-shelf or reusable systems or components. It is basically the same or similar approach as in functional safety in the way that a supplier providing reusable software or hardware component for cybersecurity item, it needs to specify the requirements, the type of work products which are affected by that. So this is more or less the same or similar mindset from the functional safety, from the ISO 26262. It's only that in functional safety, this is more refined and the standard differentiates in between different types of reusable components. These are the three ones here mentioned here. And in the end, so management, yeah, this is very important in regards to 21434. As a matter of fact, 21434 is a standard rather focused on management than on engineering. I chose to do all the presentation about the technical aspects and about the engineering aspects because I found that more intriguing and more interesting and more challenging. But this is rather a management standard. So cybersecurity management is indeed very important. It strongly relies on existing quality management standard and on existing quality processes already established, already existing in the company. That's why it's probably that the company having a quality management process already in place, in the best case also a functional safety process in place, it could achieve very easily CSMS certification and also implicitly cybersecurity certification, so the 21434 compliance. In the end, a couple of conclusions about everything, so about both of the aspects, engineering as well as management. As we saw, so threat scenarios are essential because the whole analysis starts with that. A robust, a solid set of threat scenarios basically determines all of the analysis afterwards. One of the important aspects on that is how to take care not to explode the number of scenarios and the number of cases, and how to bundle them together or how to consider them together in the HARA, because if not, this could end up in a very high number of individual threat scenarios to be considered with individual attack paths, which can be very complicated and time consuming. There are so far considered, or at least in my experience, there are considered only direct attacks. Indirect attacks, they're not considered so far, or they have rather lower priority. Obviously, due to the fact that the number of combination could be very, very high. And yeah, all in all, the 21434, as mentioned here, is rather a process standard than a product-oriented standard, strongly relying on good quality management processes, as I mentioned. Yeah, that being said, sorry for keeping you so long. So I conclude my presentation, and I may give the word back on Sven.
Okay, so at first, thanks for this presentation and to give us an overview about your results and to compare the two different standards. I think it was very interesting. And we received also interesting questions. So let's start with the question and answer session. At first, you mentioned on one of your slides the different sizes of the two standards for functional safety and cybersecurity.
Yes.
Means this the smaller size for cybersecurity that the complexity of this topic is smaller compared to functional safety, or do you think that there are other reasons?
No, that's because the management effort is far smaller. So the technical complexity for sure not, but the management effort it's far smaller than for functional safety.
Okay. And could it also be a reason that the functional safety standard is just quite older and maybe the security standard must be extended in future? So you mentioned
Definitely,
also some parts which needs to be defined more
definitely,
detailed. Okay.
definitely, yeah.
Then the second question is the process which is described in both standards, how to handle in practice the topics of functional safety and cybersecurity are very structured. We received a statement from one participant that he makes the experience that today's projects are handled very chaotic, and at the end, it happens very often that the releases will be done by so-called management releases.
Yeah.
The question related to this is, what, from your perspective or your experience, would be the consequences if an automotive company don't follow these standards?
Well, yeah, first of all, if a company doesn't follow this standard, it doesn't necessarily mean that they are unsecure. Yeah, by the way, as I mentioned here, so you can still be unsecure even when complying to this standard. But the first consequences means that implies that the company doesn't, to say so, speak the same language as the other companies following these standards, and it will be far harder for them to negotiate the interfaces and the contracts with the suppliers because they don't have standard interfaces, they don't have standard terminology, they don't have standard documents, they don't refer to standard roles.
Mhm. Okay, thanks for answering this. The next question is maybe also related to this a little bit, how the standard conformity will be proven.
This will be proven in a similar manner as for functional safety assessment. So it should be performed a cybersecurity assessment. So there are also the typical, I think I mentioned here in the previous slide, management. So the main documents in cybersecurity in 2144 management are the plan, the cybersecurity plan, and the cybersecurity case. And at the end, all the stakeholders who need this CSMS certificate, they have to deliver cybersecurity case listing all the documents, all the work products prescribed by the standard and required by the standard with the argumentation how this fulfills the cybersecurity of the item. And once you have this, and once this is assessed by a third party or by an independent assessor, then this will be proved. That means that you are 21434 compliant. That doesn't necessarily mean that you are completely secure.
Yeah, for sure. Okay, thanks to that as well. Now we received a question which is really interesting. In terms, we have contradiction between functional safety and cybersecurity during discussions or clarifications. What do you think, who will be responsible to judge or resolve such kind of topics?
So are those contradictions referring to the existing definitions in both standards, meaning that they are defined in the standards in a more or less incompatible way, or how should I understand those contradictions? Or are they contradictions in this presentation? Or
No, I think so. It's my interpretation now, but I think it's more from the doing side. So if we, for example, evaluate risks or analyze products with a view of both sides, there could be in between the both interests, there could be contradictions. I would say it's more in a technical perspective, maybe.
yeah, maybe if we took, for instance, some street release. So for the time currently, a street release for a road clearance for a certain function, for a certain ECU or for a certain car. It may depend on some safety aspects. So the same could be for cybersecurity, and they may contradict that. For instance, yeah, one release manager could say that, I don't know, he needs earlier based on some safety clearance, whereas the other may consider it differently. I think they should be kept, first and foremost, I think they should be kept as separate uh, departments and separate teams within the companies. And this is what more or less all the current customers tend to do right now, at least from my experience till now. But they should interact in between at different moments in times. And those moments in times, unfortunately, in my view at least, unfortunately, they are not so well depicted in this 21434. They were better depicted in this J3061. But those interfaces, they should be basically done in a sort of a standard way. That means that people with safety background, they should be trained in regards to cybersecurity, and also people within the cybersecurity team, they should have at least a basic functional safety training. But they should be kept separate, having clear and well-defined interfaces. This is my view on that. I hope this answered this question quite.
Yeah, and I agree totally with your meaning. For me, it's also very important that both teams interact together and to bring such problems on the table and find, hopefully, together a solution for the product finally. You just started to make to go to the next topic, I would say. So a next question would be, what if you think on a guy who is very experienced in functional safety, but not so much in cybersecurity. So what do you think are the knowledge gaps generally, and how, or has you recommendations how these knowledge gaps can be filled, or tips on training for functional safety engineers to come also into the cybersecurity topic?
I think the very first thing to be understood by the functional safety people in regards to this standard, to 2144, is that this is essentially a management standard, and that people which were already familiar and already doing functional safety management, that should be easy for them to understand this standard, provided that they attend the training. And I think the very first step should be in regards to management, and should not focus that much on the technical aspects. They should not be so much thinking that they have to have, let's say, deep technical understanding of some cybersecurity aspects or measures, because this is essentially a management standard.
Okay, thanks. Then the next question. I'm not sure if you just heard about, but there is mentioned in methodology, which is called MILS. This stands for Multiple Independent Levels of Security. And the question is, if you just heard about it, can methodologies like this be used in a risk decomposition similar what's used in functional safety.
Yeah, that would be a good point. I'm not sure if in cybersecurity you can assess the independence of uh, of risks to two different components in the same manner as in safety. Therefore, I would be reluctant in saying that this could be taken over, but I'm not very familiar with this method. And apart from that, yeah, this is not ISO standardized.
Mhm.
So this may drift away from this from the 21434 compliance. As a matter of fact, the CAL levels, the assurance levels in cybersecurity are informatively recommended.
Mhm. I think it's an interesting topic, which maybe we can also think about later on.
Yeah.
Yeah. The next question is for cybersecurity. I'm not really sure if it's in functional safety as well, but could be from my point of view. Can you say something how to calculate the residual risks?
Pardon, could you repeat the question?
Yeah. The question is, can you say some words how to calculate the residual risk that will be left after the development of the product is finished?
In cybersecurity,
Yeah,
yeah,
mainly.
that's the whole point, because in cybersecurity the risk has to be managed. It doesn't have to be reduced to some minimum level. This aspect with the minimal residual risk is it has also a lot to do with the risk related to hardware and to hardware reliability, and is mainly coming from there. And this has a lot to do with this fault rates for hardware components, and something like that. That's not possible in cybersecurity. You have to manage it, and it's always about the cost benefit analysis.
Thanks for that. There was an additional question. So in the ISO 21434 standard, there are 3 risk matrices are given for risk calculation, which can be used. The question is, should this be decided based on ECU ASIL level, for example, or should it come from the OEM? Which of these methods are used for the risk calculation?
Um, what exactly was meant with these three methods?
I think there is, I'm not
So the
100% familiar with the standard, but I think there is something mentioned like you can use CVSS for judge the risks or the vulnerabilities finally, and there are 2 other
my take on that,
methods.
my take on that is that those are recommended by the 21434. So, in order to determine, so in this case, for this common vulnerability scoring system, so this CVSS for the attack probability, this is this is. This is only a recommended method by the standard, but I think the OEM is free to pick up another standard. I think this is ISO standardized, this method, and that was simply referred by the 21434 as an example, only as a suggestion. But I
Yeah,
think the OEM it's free to implement to take another one, and also it's free to pick up the numbers for different aspects of this attack feasibility completely differently. Yeah, and also even to consider different aspects of attack feasibility. So not only the four ones which I mentioned in this example. So about the knowledge of the item, the equipment necessary, the knowledge of the attacker, the time window.
Yeah. But do you think the OEM should decide this and all suppliers for this OEM has to follow it, or is it up, for example, for the company itself?
It's coming top down. I think this should come top down from the OEM.
Okay. So then this was all questions that we received. I think if you look on the timing, it is also a good point of time now to coming to an end.
Yeah.
I would give you the chance to say some final words to the audience.
Yeah,
Please go.
thanks. Thanks, Sven. Yeah, thanks a lot to everyone, and thanks for watching my presentation, for attending this meetup. I hope you found that interesting and challenging. So please come to us, come to me whenever you would have questions. Also, when you would have some project issue, or when you may require help in this regard. So you can write me an email, you can contact me per LinkedIn. That's absolutely no issue. Yeah, and for those of ones celebrating the Easter, so happy Easter to all of you celebrating it.
Okay, so as well from my side, again, very thanks to Bogdan. This was a very nice presentation. And I hope also the audience enjoyed it. Or I'm sure that they enjoyed it. We got also some positive feedback from the audience directly during the presentation, which I can also forward to you, Bogdan. Also thanks for our technical team. So today we had Pascal, which takes care that everything is running fine. Also thanks to you. And to the audience, I hope you enjoyed today's presentation. And I hope we see us again in one of our upcoming webinars. And also from my side, to whom which is celebrating the Easter, have a happy Easter vacation and see you soon. Bye bye.